So first thing is first, we're flashing back to chapter 9, which felt like a decade ago. And we are going to talk about mass spec and NMR. I actually don't know why I put mass spec first. That might have just been a mistake, but since we have it here, let's go over it. So mass spectroscopy is basically used to find the molecular weight. And when we have the molecular weight, we can figure out the formula. And the way it works is by using high energy beams to break the molecules into radicals. So one example we talked about earlier in the semester was this. And when we break it apart, we end up with this. Okay, cool. Sorry, I just got like a private message. So once we get this radical, we are going to figure out different things about our molecules. So first things first, let's talk about the 4 main aspects of mass spec. So this is very different than NMR, but for mass spec, we're going to talk about the tallest peak, which is the base peak. The base peak has the highest intensity / abundance. So it's the tallest peak in the whole entire spectrum. The M plus peak, which is the parent peak, is the unfragmented radical. So it's the whole molecule itself. And that's going to represent the mass of the whole molecule. The M plus 1 peak represents the isotopes of carbon, hydrogen, and nitrogen. And I just want you guys to know that the biggest or most important or most significant contributor for the M plus 1 peak is going to be carbon, not nitrogen or hydrogen. It's going to be carbon. Also, Roche's students, no, I put this in the beginning. I decided to start with chapter 9, so you don't have to pay attention to this part. It shouldn't take more than a minute or two, but you guys don't have to worry about it. All right, for my West students, M plus 2 is for oxygen, sulfur, bromine, chlorine. Oxygen and sulfur are super tiny, almost insignificant. Bromine and chlorine are the ones that are important. So bromine has a mass of 80 on the periodic table. However, the mass of the 2 isotopes of bromine are 79 and 81. And they are at a 1-to-1 ratio. So there's equal amounts of the 2 isotopes in nature. So what that means is the M plus 2 peak will be the same height as the parent peak if bromine is in your molecule. For chlorine, if chlorine is present, the M plus 2 peak is going to be 1/3 the height of chlorine. I'm so sorry. If chlorine is present, the M plus 2 peak is going to be 1/3 the height of the M plus, aka parent peak. Okay. So it says here, do not use 80 as your mass for bromine. 80 is the average. Use 79 and 81. And what this means is if you're calculating the mass of a molecule that has bromine in it, in order to find the M plus peak, you use 79 for the mass. In order to find the M plus 2 peak, you use 81. If you ever see an odd M plus peak or an odd number for your total mass, that always means that we have an odd number of nitrogens present. So remember, odd number of nitrogens. 2 nitrogens won't be odd. It will actually be even. So sometimes he'll trick you and put 2 nitrogens, and you have to know that that would be wrong. If he asks you a question that's something like, what is represented by a -17 or a -18 peak? All that means is you lost an OH. The reason it can be 17 or 18 is because you can lose it as OH or you can lose it as H2O. That is it for mass spec. If anyone wants to know any more about mass spec, we covered it in more detail earlier on in the semester. So I do have an SI video of it up on YouTube. And I also have a mass spec concept video on YouTube. So you can definitely look back and check on those. Roche's class, again, you can kind of not worry about that. All right, that was a huge mouthful. Questions, comments, concerns on mass spec? Going one?
Could you just quickly re-explain how the OH can be lost with a hydroxyl radical, like with the -17 and the -18?
Yes, so all you really need to know here is that OH is kind of finicky sometimes. So sometimes it can just leave as an OH group, how it usually does, or it can steal one of the hydrogens from the molecule and come off as an H2O. So let's say we had this. You could either fragment it into that, or you could fragment it into that.
Okay, thank you.
You are very welcome. All right, cool. So moving on to NMR. NMR is NMR is basically when you apply a magnetic field and you measure the absorption of a molecule. So anything more than that is not really relevant for you to know. The information that this tells you is the carbon-hydrogen framework. So you're learning about structure. So far we've learned about IR, mass spec, UV spec, and NMR. So NMR tells you structure, IR tells you functional group, mass spec tells you the mass, and UV spec tells you the level of conjugation. So the criteria to be NMR, basically all the NMR stuff I have filled out for you because we covered this a bajillion times, but I know it was a long time ago. So rapid fire review, criteria to be NMR active, you have to have spin. So what spin means is you have to have an odd number of protons and or neutrons. So you have to have an odd number somewhere. So if we have carbon 12 and carbon 13 and we compare the two, carbon 12 has 6 protons, 6 neutrons, not an odd number in sight. It is not active. Whereas carbon 13 has 6 protons, 7 neutrons. We have an odd number in there. Therefore, it is active. Yay. As far as what solvent and calibration standard we use, the solvent is a deuterated solvent, usually CdCl3, and the calibration standard is TMS, and this serves as a 0 point. So yeah, there's not really too much to explain. And then someone said Katrina uploaded the final exam review to her Canvas page. I don't know if she uploaded this same one or her own one, but Katrina's amazing. So, all right. So the 4 aspects of NMR are the number of signals, chemical shift, multiplicity and splitting, and integration. And so at this point, we know that number of signals is just counting signals. Chemical shift is the ppm values. So those are the chemical shift regions. And all that tells you is where the peak is on a spectrum, which is just relaying how shielded or deshielded it is. The multiplicity and splitting is telling you about the neighbors and the different environments. So we have a couple rules here. So we are not going to split through a heteroatom unless we have a pure solvent. So both professors said kind of different things. So go by what your professor said, but the main takeaway is you are only going to split through a heteroatom if you have a pure sample. The other rule is n+1, and we know that normal splitting and complex splitting are slightly different. So normal splitting is n+1, and complex splitting is actually n+1 times n+1. And we're going to talk about that in just a second. Integration just purely means how many hydrogens there are per signal or how many carbons there are per signal. I would like to point out number of signals, chemical shift, and integration are for both nitrogen and carbon NMR, but splitting is only for hydrogen NMR. You cannot do splitting on carbon NMR. All right.
Did you mention something about a pure substance? What was that again?
Yeah, so you are only going to split through a heteroatom if you have a pure sample.
Okay.
Okay, and he would have to just say it like that. All right, so counting signals, again, these are things we've done a couple times in the past, and I do have a video about it, so we're kind of going to speed through it. What I want you guys to really focus on is symmetry and environments in 3D. So anytime we have a ring, we are going to be able to look at the different environments in 3D. So let's say we have two OHs, whether they're cis or trans, you're going to get different ways of putting your molecule together. So if they are cis, let's say they're both pointing up, all of the hydrogens pointing up will be the same. All of the hydrogens pointing down will be the same, but the hydrogens pointing up and the hydrogens pointing down are completely different from one another. If we have one that's pointing up and one that's pointing down for the OHs, then we get this crisscross pattern where these two on the top correspond to these two on the bottom, and these two on the top correspond to these two on the bottom. In addition, one that you see pretty often is these guys. So if we have two methyls pointing in the same direction, these two hydrogens will be completely different because one sees methyls, one sees hydrogens. But if they're pointing opposite directions, this effect like balances each other out. Both of these hydrogens see the exact same thing. Therefore, we only have 3 hydrogen signals. All right. The last part of counting signals is homotopic, heterotopic, diastereotopic, etc. So, homotopic, heterotopic, those are really simple, straightforward umbrella terms. Homotopic, same, heterotopic, different. All there is to it. So, anytime there's 2 hydrogens that are part of the same signal, they're homotopic. If they are different signals, they're heterotopic. 2 more specific categories that we could have is enantiotopic and diastereotopic. So enantiotopic is part of homotopic. If a signal is enantiotopic, it is still one signal. Those 2 hydrogens are exactly the same. Nothing changes. It just has a different name. And this happens when we have a potential chiral center. And that potential chiral center does not have any other chiral centers. So, sorry, I lost my train of thought because of the sound. I don't even know if you guys heard it. Anyways, it's fine. Yes, okay. So I think we're pretty much done with enantiotopic. If anyone doesn't know what a potential chiral center is, that basically just means that there are 2 unique groups and 2 hydrogens on the same carbon. All right, switching it over to diastereotopic. So diastereotopic, there's 2 different ways it could happen. One is chiral centers and one is double bonds. So if we have a chiral center present on a molecule, every other potential chiral center turns into diastereotopic. And I will say that again. If we have a chiral center present in a molecule, every single other potential chiral center is diastereotopic. One more time for good measure. If we have a single chiral center anywhere on the molecule, every single potential chiral center is diastereotopic. If we have a double bond, we have two rules that we have to follow. The two hydrogens in question must be on the same carbon, and the other carbon needs to have two different groups on it. The first one I have drawn has a methyl and a hydrogen on one side, and then I'm pointing to two hydrogens that are on the same carbon. Therefore, those two hydrogens are diastereotopic. In the second one I have drawn, HA and HB, there's two hydrogens on the same carbon, cool, but carbon number 2 has two of the exact same groups on it. Therefore, this is symmetrical and they are exactly the same, so we can only use the term homotopic. The other example that we have, I'm not going to redraw it, but if we have this, let's say we're comparing the black hydrogen to the pink hydrogen, their relationship is going to be heterotopic because the two hydrogens are on completely different carbons. So they could not be diastereotopic or homotopic. Excuse me, diastereotopic or enantiotopic. All right, so that wraps up counting signals. Questions, comments, concerns?
For the one you just mentioned, the hydrogen across the dotted line and the pink hydrogen, what was the relationship? Was it homotopic?
Heterotopic. Good question. So I will write that in for you. So these two are heterotopic. I just realized my boba's been peeking out of the corner the whole time. This session is sponsored by Boba Street Cafe. Come in and try some boba today. I'm kidding, I'm not sponsored, but I should be. Okay. No more questions. We are moving on. Just kidding. Yes.
You see that triangle you have on top left? How are those signals different? Because I just want to write it down.
Okay, so for this one, the two methyls are pointing up. So the hydrogen that is pointing up is seeing two methyls, whereas the hydrogen that's pointing down is seeing two hydrogens.
Okay.
So they're completely different.
Oh, okay.
Oh,
and the
thanks, Sarah. You're so sweet.
No
and the
question.
other one, to the right of it, it only has 3 because those two H's are seeing one H and one methyl, right?
Exactly.
All right, so they're the same. All right, thank you.
You're welcome. Okay, someone else had a question? Yeah.
Yeah, so back to like the diastereotopic. So I understand like you said has two chiral centers, but let's say for example there's already okay for diastereotopic there already has to be one chiral center already there. But so let's say like there's the two hydrogens and then like it doesn't create a new one. Does that make it like an anterior topic, or does that make a homeotopic?
So I don't exactly understand what you're asking. So I'm going to say draw it out, send me an email, and I will respond to your email. Okay?
Okay.
Okay, cool. All right, so next up we have chemical shift, and I already did this for you because we did the same exact thing a little while ago. So the chemical shift equation is ppm equals hertz over megahertz. We also do times 10 to the 6 technically, but we're not going to do that for the purpose of this class. Don't ask me why, just that's the answer. So if he gives you a question, it's going to be something along the lines of 40 megahertz, 1.25 PAPM, some amount of hertz, whatever. So all you're going to do is substitute that equation. So for example, if they give you megahertz and ppm, you do ppm equals x over megahertz, you multiply the two and you get 500. If they leave out the ppm, you just do whatever hertz they give you over whatever megahertz they give you, and you get the ppm value. This one's pretty much just simple math, so I'm not going to stay on it for too long, but does anyone have any questions? Swag.
Would they ask you,
Yeah, what's up?
for the Hertz question, would they just ask you like either of the three, or would they just ask you just like the Hertz?
They'll ask you either of the three.
Okay.
Okay. Cool. So this stuff, chemical shift, is honestly less stuff that I can explain to you, more just memorization. So I will leave this up for you. The biggest thing that I want to tell you is heteroatom region. Remember that for hydrogen NMR, you could either be on the heteroatom or one carbon away. And I also want you to remember that HNMR and CNMR are a little bit different when it comes to the carbonyl region. So carbon NMR includes aldehydes, ketones, and carboxylic acids, whereas hydrogen NMR, ketones are under the alkyl region. The carbonyl region is strictly for aldehydes and ketones. And that's pretty much all I have for you. We can do these examples, and it is a little bit different. So we have 1, 2, I'm going to do this in normal numbers actually because I hate Roman numerals. Okay. Can I repeat it? Yes, I'm guessing you mean about the carbon versus hydrogen NMR thing. So for carbon NMR, the carbonyl region includes aldehydes, ketones, and carboxylic acids, whereas hydrogen NMR, the carbonyl region is strictly for carboxylic acids and aldehydes. The alkyl region is what has the ketone. Okay, so putting these in order, we're going to get a different answer in the carbon and hydrogen NMRs. That's why they're in two different lines. So the carbon NMR, we're looking at the most deshielded carbon for each molecule, and we're going in decreasing order. So we're going to go from most deshielded to least deshielded. So the most deshielded is actually going to be 2, and then we have 5, and then we have 6, 4, 1, 3. However, for hydrogen NMR, 5 is by far the most deshielded. And then we have 6, 4, 1, and then 2, and then 3. Again, I have a video on this if you need more in depth about how/why this happens. But for this review, this is pretty much as deep as we're going to go into it. And we are done with chemical shift. So do we have any chemical shift questions? Cool. All right, moving on. So spin, splitting just means anything higher than singlet. So we're looking for doublet or higher. So the first thing I look at is this guy, 1, 2, 3 bonds. So they have a neighbor. So yes, that shows splitting. For the second one, there is a line of symmetry down the middle. So these two H's are exactly the same. They are not neighbors. This does not have splitting. The one on the bottom, again, exactly symmetrical. But this hydrogen and this hydrogen do split each other. So that does have splitting. This H and this H cannot split from one another because 1, 2, 3, too many bonds, and there's an O in the way. So this is not showing spin. The last two, 1, 2, again, way too far away, does not show spin splitting. For this one, we have 1, 2 hydrogens, 1, 2, 3. They are within 3 bond lengths. They are neighbors. So, ta-da, they are in fact showing spin splitting.
One question.
Yeah.
One thing I have issues with for splitting is the one that's like in the middle on the bottom with the OH. So how is the one in the middle different than all the ones on the side, like for the methyls? Like, is there not a hydrogen right there, right in the middle?
No, so there's 3 hydrogens. There's 3 methyls, which means that that carbon is fully substituted, which means that there is no way it could have a hydrogen.
Okay, I got you now.
Okay, cool.
Wait, so to confirm, right? When it's symmetrical, the two hydrogens that are symmetrical to each other, I guess, they don't count as neighbors. Like,
No, so if the hydrogens are homotopic or symmetrical, they don't count as neighbors. They are just one signal.
right.
That's a good question. Coolio. Alrighty. Okay, cool. So I'm going to assume we don't have any more questions. And I am purely just going to give you the J values because it's just a lot of memorization. Geminal and vicinal are the easy ones to remember. So vicinal is 7, and that's a normal splitting. Geminal is 12 to 15. Equatorial is 2 to 5. Equatorial axial is 4 to 6. W coupling is 0 to 2. Axial is 11 to 14. And I do want to make a distinction. So some people were upset with me because of something that I said about geminal coupling, and then people got it wrong on their exam. So I do want to tell you. Geminal coupling only has a J value when they're diastereotopic. If those two hydrogens are homotopic, the J value equals 0. So it is only 12 to 15 if they are diastereotopic. While you guys write this down, someone asked, is spin splitting the same as complex splitting? So no, those are not the same thing. Spin splitting, all that means is that we have a multiplicity higher than a singlet. Whereas complex splitting is like entirely different. What if they were geminal on the end of the double bond? Again, it entirely depends on whether they're diastereotopic or homotopic. Okay. So normal and complex splitting, we took a long time to go through and talk about this. We're just going to do the fast version right now. So normal splitting is when we have all the same J values, and how I want you to think about it is hybridization. So if we have all the same hybridization, that is normal splitting. So we're just going to count all the neighbors and add 1. So we are specifically talking about the red hydrogens And I actually made a mistake. This is also supposed to be a hydrogen. So please correct that in your notes. So the 3 hydrogens, which are red, are going to have 2 blue neighbors. So 2 blue neighbors plus 1 equals 3. This is a triplet. Complex splitting is when we have different hybridizations. So the red hydrogen is sp2, the blue hydrogen is sp2, and the green hydrogens are sp3. So we're going to do the left side plus 1 multiplied by the right side plus 1. So we have 1 neighbor plus 1 multiplied by 2 neighbors plus 1. So this turns into 2 times 3, which equals 6. So this is a doublet of triplets. So apparently it says sextet for the left one. That was before I changed it into a hydrogen. But there was a problem in that, so it was supposed to be deleted. I must have sent it to you before I erased it, so I apologize. But do it the way that I just showed you now. Okay, so the last type of complex splitting thing you might get is this whole theoretical complex splitting. So it gives you something and it says, theoretically, imagine that JAB does not equal JBC. So you have to find the splitting for the hydrogens on carbon B. So we're going to do 3 neighbors plus 1 multiplied by 2 neighbors plus 1. So you get 4 times 3, which is 12, aka triplet of quartets. I know we went through that super duper fast, but any questions on splitting of any kind?
Yeah, how did you know? Oh, actually, I just read the question. It says B, right? That we have to split.
Mm-hmm.
Okay, never mind. Thank you.
You're very welcome. Okay.
So is the hybridization different for A and C,
For
or
this one, it's actually not different. He's just saying theoretically, if it was different, what would you do?
oh, so theoretically if the hybridization was different, I guess.
Yep. And
Oh,
why is it a quartet? Why is it a triple of quartets and not a quartet of triplets? For the purposes of this class, those things mean the same exact thing. Either would be correct.
so would he like because you know how like it seems like maybe like a multiple that equals up to 12. So like would it only be like a triplet of quartets, or like like a doublet of like sextets, you know what I'm trying to say, or would he not have in the exam?
It's specifically going to be whatever you get here.
Okay.
So we have 3 plus 1, 2 plus 1. So that's where we get these from. So triplet, quartet.
All right. Thank you.
You're welcome.
So is the not equal sign telling us it's complex splitting? Like assuming complex splitting? Okay. So if it was telling us to do normal splitting, would we just have an equal sign? Or
Exactly.
So like, since it says theoretically, right? If it was actually unequal, there would be a double bond between one of them, right? Like B and C.
Yep.
So we don't
Yep.
have to like assume that and like, I don't know, subtract a hydrogen or two.
No. He's just saying pretend that they're not equal and you don't have to do anything else besides complex splitting. Don't take away a hydrogen or anything.
Oh, okay.
Julio. All right, so this is just here, write it down, take a picture, whatever. All he's going to ask you is what does COSI stand for? What does det core stand for? What does het core stand for? So just know that we're not going to spend time talking about it. We are done with chapter 9. Any chapter 9 questions? Swaggy. Chapter 11. So chapter 11 was one of those annoying chapters. So first we're going to talk about physical properties. So boiling point. Boiling point. Alcohols have a higher boiling point than ethers do. That's what that arrow means. And the higher the boiling point, the less branches. So higher BP, lower BP. Not blood pressure, boiling point. Same exact trend here. So we have a higher BP, lower BP. More splitting, more branching, lower boiling point. Acidity, this is something we've talked about all semester. It keeps coming back. So the question, the first thing I have there, I'm sorry, I got so excited. The first thing over there is just to show you what the conjugated base of an acid is. So the conjugate base is just when we take off a hydrogen and it gets a negative charged. So the conjugate base of an alcohol is called the alkoxide ion. And yes, I can scroll back for a moment. And yes, this trend is exactly the same for alcohols and ethers, more branch to lower boiling point. Swag. Okay. So order of acidity, we've added to our order that we had, but I want you guys to remember, if we take it back to the basics. Oh. Someone sent some long link and I got very much distracted. Anyways, so B is the most acidic. D, not B. B, A, C. There is a video about acid trends. So if you don't understand acids and bases, please watch that video. So identify the strongest acid and strongest base. So this is really a concept question. And they want you to know that more electronegative equals more acidic, less basic. So between the O and the N, the O is the better acid, the N is the better base. So we have acid, base, conjugate, acid. So this is the strong acid and the strong base. Ta-da. We're done with physical properties. Any questions? Swaggy. Protecting groups.
How do you know?
How do I know? How do I know?
I don't know. Honestly, like the whole acid and base thing, I've like heard it like 100 times. I still don't get it for some reason.
Okay, so I will send you something for that.
Okay.
And I know someone wants to take a picture, so that's kind of why I left it over here for you. Please don't screw up. Okay. Ta-da. Watch that. Okay, so we are going to move on, but I'm not just annoying. I sent him a link to watch. Okay, so protecting groups. We have done protecting groups about 4,000 times, and trust me, I understand that they're annoying, and it feels like everyone just dumped it out of their head the minute they got out of that first exam. I feel that. So I want you guys to remember PBr3 or PCl5, SOCl3, SOCl5, all those guys, they are all going to turn OH into a heteroatom. This is an SN2 reaction, so it's going to flip the stereochemistry. When we turn it back to an OH, or anything for that matter, it's also going to be an SN2 reaction. We're going to flip that stereochemistry again, and we are going to overall retain stereochemistry. If we have mesylate or tosylate, we are going to keep the stereochemistry in the first step, and we're going to flip it in the second step. Since we only flipped it once, it ends up overall flipping the stereochemistry. And the way he might ask you that in a question is like what I have drawn right here. And the answers are written there. So any questions about protecting groups? Swaggy. Okay. Dehydration of alcohols. So basically, I want you to know that H2SO4 and POCl3 are the two different types of dehydrations we're going to do this semester. H2SO4 is E2. POCl3 is E1. This has rearrangements. This does not. So we would get the most stable possible double bond for this one. Just kidding, I added an extra methyl. I'm sorry. However, for the other one, we are not able to move anything around, but in this case, we do get the same answer. There is another example on the handout that I have for you guys. They are slightly different, so it's easier to see the difference, but you can look at that whenever. So ethers and epoxides, when it comes to, we'll do making first because that just makes more sense. So when we're making ethers, we have the Williamson ether synthesis. We are going to react an alkoxide with an alkyl halide to make an ether. And then for making epoxides, we could either do the intramolecular Williamson ether synthesis, or we can react an alkene with a peroxy acid. And remember what I said about peroxy acids. Anything that has O3 is a peroxy acid. That's pretty much it. For breaking ethers and epoxides, it's a little bit different in acid and base. So ethers, cyclic or linear, are stable in base and reactive in acid. And in acid, the order of reaction is 3, 1, 2, because it's a pain in the ass. For breaking epoxides, still a pain in the ass. But in a base, we're actually going to go 1, 2, 3. So the way I remember this, acid, pain in the ass is in a really weird order. Bases are basic bitches. They go the same way the number line does, 1, 2, 3. That's how I like to remember it. Don't report me. Thanks. Have a good day. Crown ethers. I don't think Dr. Roche ever talked about this, so RIP Roche students. But for my lovely Dr. West students, all you have to do to name these guys is do blank, crown, blank. The bigger number is always going to go first, and the smaller number goes second. The smaller number is the number of oxygens. So here we have 4. The bigger number is number of O plus C. And instead of sitting there and counting, you can always do number of O times 3, which is 12. For the second one, we have 1, 2, 3, 4, 5, 6. 6 times 3 18. So 18 crown 6. Questions, comments, concerns?
For the breaking ethers, it says there's no reaction for the base on the sheet you put on canvas.
Yes, there's no reaction. It's stable.
Oh, okay, so it's stable and no reaction the same then.
Yeah.
Okay, cool.
Coolio. So we're going to do a couple different reactions, and I'm not actually going to go through all the steps. So if you need help with all the steps, please refer to my YouTube videos. So this first one is just the Williamson ether reaction. So we kick off this guy, or we kick off the H actually, and then we kick off this guy, and we add those two things together. Ta-da. For the second one, it's an intramolecular Williamson ether. So we just go bam, bam, because we connect this side to this side. Peroxy acid. We replace the double bond with an O. The reason I have trans thingamabobbers is because we had a trans double bond to start with. Substituents, that's what I meant by thingamabobbers. When we have an ether with acid, we can either have it with regular acid or we can have it with excess. So if we have regular acid, we're just going to count 1, 2, 3, 4, 5. We make a thing 1, 2, 3, 4, 5, 5-membered chain. We're going to say this is 1. We're going to say this is 5. And we are going to break it open. The order that we want to break it open in is 3, 1, 2 because it's a pain in the ass, right? We choose to attack carbon, the primary carbon, which is carbon number 5, which means Br is added to carbon number 5. And on carbon number 1, we have a methyl and an OH. The only difference between this and excess is that we also replace the OH with a bromine. So if we have excess, we have 2 bromines. If we don't have excess, we have 1 bromine, 1 OH. For breaking epoxides specifically, we're going to skip this first one because it doesn't matter. For the second and third ones, we have stereochemistry. One has acid and one has base. So the one that has acid is the H+. The order is 3, 1, 2 because it's a pain in the ass. Whew. All right. So we are going to attack the tertiary side. So it's going to open up to the primary side. So we get OH, and we are going to keep the stereochemistry on the side we open, and we're going to flip the stereochemistry on the side we attack. I'll say it again. Keep the stereochemistry on the side you open to, flip the stereochemistry on the side you attack. The only difference with the base catalyst is the basic bitch. It goes 1, 2, 3. Therefore, it's going to open the other way around. So you end up with the OH on this side and the OCH3 on this side. Questions, comments, concerns? And we're going to skip this one too because it's more of the same thing. So bam, I zoom out.
Never mind.
What about like the NaOH and the peroxy acid? Like why did it like what happened there? Like the other stuff broke the rings open, you know?
These are making epoxy.
Oh, okay. No, I was gonna say they look like different things that are happening. Okay.
Yeah,
That makes
so the
sense.
top of it, yeah. Swaggy, we're done with chapter 11. Oopsie. Technically, oxidation and reduction is kind of a mix between 11 and 12, but that's fine. Yeah, fine. dehydration right quick. We're going to zoom away now. Okay. You're very welcome. All right, so we are done with the first hour, which means I'm sending you the thing again. Nope, I sent the wrong thing. Frick. Tight time frames are not good for me. They just make me panic. So I'm sending the thingamabobber again. Please sign in. Thank you. Okay, yes, so we are in 11 and 12. This one's kind of like a mix between the two. Oxidation reduction. I was going to wait for you guys to sign in, but I am impatient. So we're just going to do the thing. Oxidation, making more bonds to oxygen. Reduction, reducing the number of bonds to oxygen. So they are complete opposites. For reducing and oxidizing agents, oxidizing, we have weak and strong. Weak is PCC and DMSO. Strong is anything that has 4 or more oxygens present. Reducing agents, we have weak and strong again. Strong is LiAlH4. Weak is NABH4. The way I remember this is stupid, but A comes before B in the alphabet. Therefore, A is obviously the stronger one. Diba, or dibol, is a strong, weak reagent, so it really should be in the middle. It only reduces esters and carboxylic acids, but it stops at the aldehyde. It doesn't go all the way to the alcohol. And then, last but certainly not least, the reducing agents are these guys. The reducing species are always going to be H-. So the reducing species are always, always, always H-. This is the thing. Absorb, take picture, do what you do.
What's below the carboxylic acid on the right, all the way at the bottom, because it kind of cuts off on our page. Oh, okay, thank you.
You're very welcome. And then if you're sitting here like this was not a good enough explanation of oxidation reduction, that video is for you. I hope you have the best 32 minutes of your life, but we are going to move on right now. Questions, comments, concerns? Bless you. Swaggeroni and cheese. Let's go. We are on chapter. I'm so sorry. So chapter 13 is all about conjugation. That 32-minute vid was fire. Fuck yeah. Whoa, I don't know why I said that. So conjugation is basically when you have one double bond, one single bond, one double bond, one single bond. So it's 2 double bonds separated by a single bond in the middle. So isolated means 2 double bonds with more than one single bond in the middle, and cumulated means 2 double bonds on the same carbon. And so the most stable is conjugated, and then we have isolated, and then cumulated is garbage. Okay, so configuration versus conformation. This is kind of I don't want to say easy, but it's one of those straightforward things that you just kind of know. So again, we are going to scoot right past it, but there, I hope you enjoy the 19 minutes and 8 seconds of your life that you will never get back if you watch that video. We are going to talk really quick about ranking the stability of dienes because that is important. There are often questions like this. So I want to start with the fact that not all of these are conjugated. So the not conjugated ones are automatically less stable than the conjugated ones. So this one and this one are conjugated. These 3 are not. They're all isolated. So we're going to figure out which one is the least stable one out of them. And the first thing that I see is that these two double bonds are at the end, and they only have one substituent. They both suck big time. So that is last place. It's a absolute loser. Super unstable. Between 2 and 3, they each have one monosubstituted and one disubstituted double bond. But if we look at the double bond, this guy has 2 groups pointing opposite directions. This one has 2 groups pointing the same direction. This one is going to be E. This one is going to be Z. That is a really weird looking Z, but just vibe with it. E is more stable than Z, so the order goes 2 and then 3. Beautiful, wonderful, magical.
Which for all of them, number 1's obviously the most stable, but it's 2. Then it goes 2, 3, 4. But what about 5?
Well, if you just held on for one darn moment.
Oh,
No.
sorry.
Okay, that's okay. So 1 and 2 are going to be the 2 most stable ones. We just want to know which one's first place and which one is second place. So
Okay.
number 1 has E, and in the middle, this guy is S trans. For number 4, the one in the middle is still S trans, but we have Z, E. Z sucks. So the one that has 2 E's is first place. The one that has 1 E and 1 Z is second place. And then it's 2, 3, 4. And someone asked, 2 is more stable than 3 because it's trans. And yes, that is true. So the trans one is better than the cis one. Or E is better than Z, we could say. Whew. That felt like a lifetime of talking. How's we feeling? Questions, comments, concerns?
So 1 and 5, they're technically both S trans, right?
Yes, they are both S trans.
So so because they're both the same, in order to find which is more stable is why we're looking at configuration instead.
Exactly, yep.
Okay, I got it.
And usually configuration is going to be more important than conformation only because you can't really change the configuration. But you can change the conformation. Cool. So UV spectroscopy, this is literally all I'm giving you for today. Enjoy this 6-minute video of me telling you way too much information about it, if you please. All you need to know, more conjugation equals more stability, which is lower energy and higher wavelength. That's pretty much it. Molecular orbital theory, everyone's favorite thing in the whole wide world. JK. Honestly, a lot of people were emailing me or coming to me and they were like, oh, I completely forgot how to do that, blah, blah, blah. Like I knew it at the time. Let me be real with you. This is another thing that if you memorize or you understand the very, 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 very basics of it, you are good to go. So all you have to know is, well, just look at this. I mean, it tells you everything. But the main like tricks I want you to know, the LUMO is always going to have 0 electrons in the ground state, and it's always going to have 1 electron in the excited state. And the allylic examples always have a non-bonding orbital, whereas the butane or any diene really is going to have only bonding and anti-bonding. Also, if you would like to know more, 20-minute video. Swag. Okay, moving on. Fine, I guess. Any questions, comments, or concerns about MO theory? Honestly, if he asks you any MO theory questions, fairly straightforward. He's not going to try to trick you. The only thing he will do to trick you, and people get very upset with me, and then I'm like, so he could ask you about 1,3-pentadiene, right? Which is the exact same thing I have drawn, except we have an extra carbon here. And people are like, oh, Rosemary, you didn't go over that one, and I failed because of you. No, because 1,3-pentadiene, this carbon does absolutely nothing. It contributes absolutely nothing unless it is sp2. Therefore, the MO diagram for 1,3-butadiene and 1,3-pentadiene are exactly 100% the same. So there you go. I get very passionate about that one. No, okay, so what I mean by that is if he asks you a question about 1,3-pentadiene, 1,3-pentadiene has the exact same molecular orbital like setup as 1,3-butadiene. And yes, basically only sp2 matters, correct?
Is that for molecular orbital theory, just only sp2?
Uh-huh.
Okay, cool.
Coolio. All right. So 1, 2, 1, 4 additions. And then we have to do the figure eight looking thing. No.
Ah, bueno.
Please.
Ujú.
Okay, I muted you. That's fine. No, you don't, basically. Also, I'm sorry, Sarah, if you need speaking privileges, just let me know and I'll fix it for you. Okay, so 1, 2, 1, 4 additions. There's not much to them, to be completely honest. The biggest or like most difficult part of it is knowing like thermodynamic kinetic and all that stuff. So we're going to talk about that right quick. This is the part where I have a little bit of an aneurysm and I tell you something and then everyone forgets it anyway, and then I cry. So don't make me cry. You, all 32 of you, will get this question. So the kinetic product is the one that has the lowest activation energy. The thermodynamic product is the one that has the lowest potential energy. We are only talking in terms of lowest. We're never going to talk about highest or nothing like that. So only lowest. The thermodynamic product is not the highest activation energy. The kinetic product is not the highest potential energy. It's only lowest. And Eric is totally right. And that's because they can be the same sometimes. So the lowest activation energy and the lowest potential energy can be the same product. Okay. Questions, comments, concerns? Does that make sense-ish? Everyone's like, no, but you seemed passionate, so we're going to let you have it, and that is valid. So, moving on. If you don't know what I mean, but you are also scared to ask because of that little episode that I just had, there is the video for it, and I go over it in way too much detail. I will talk about that in 1 second. I don't know what you're trying to say to me, Abel, but I really tried. I just don't get it. That's fine though. If you, yeah, anyway. So for the 1, 2, 4, I'm sorry, I'm having a stroke. For the 1, 2, 1, 4 reaction, we have a diene, we're reacting with HBr, and we're getting two products. The 1,2 and the 1,4 products. Wow. So the 1,2 product is when the hydrogen and bromine are next door to each other. The 1,4 product is when they are farther away from each other. So in these kind of examples, the kinetic product is the one that happens in the fewest number of steps, and the thermodynamic one is the one that has the most stable double bond. Easy. So in this example, the 1,2 product is kinetic and the 1,4 product is thermodynamic. This will not always be the case, but for the ones you get on this exam, it most likely will be. The nucleophile is always going to be A. The electrophile is always going to be B. I take that back. The nucleophile is always going to be the diene. The electrophile is always going to be HBr. And someone left. I'm sorry I scared you. Diels-Alder. This is another one where everyone is like, I remember negative information. And I'm like, that is so valid. So Diels-Alder is the one that looked super complicated, where everything was going around in a circle and we were making a ring. So link to that. The Diels-Alder reaction is between a diene and a dienephile. A diene is any conjugated diene. It is the nucleophile. It has to be S-cis, and it likes to have electron donating groups, whereas the dienephile is the electrophile. It's any alkene or alkyne, aka double or triple bond. It must maintain its configuration. So you don't have to start with a specific configuration. You just have to maintain whatever you start with at the end. And it likes to have electron withdrawing groups. Now, I hope by this point, after chapter 14 and 15, we have a good understanding of what electron withdrawing and donating groups are. But just in case, let's go back and let's talk about that. So electron donating groups have lone pairs, a lot of electron density, negative charges, or R groups. And these donate via resonance or induction or electronic effects. Electron withdrawing groups have positive charges, halogens, and just like carbonyls, big bulky groups, things like that. So in the Diels-Alder reaction, I'm also going to send you guys this little like one-page summary of Diels-Alder that I made, because it's pretty helpful, I think, and it includes everything you really need to know about Diels-Alder. Basically, I want you guys to know that we're always making a 6-membered ring, and we're always connecting carbon 1 to A, carbon 4 to B. And the other trick that I often use is if we start out with a 5-membered ring like this one, we end up with 1 carbon in the bridgehead. If we started with a 6-membered ring, we would have 2 carbons in the bridgehead. So that's how you kind of, that's what you kind of should pay attention to. So someone asked, can a Diels-Alder reaction with just a cyclic butadiene and heat? So you're talking about this guy, and it can cyclize with itself. I forget what that's called. It's fine. It's going to end up making this. Ta-da. Don't worry too much about it. You will most likely not be tested on this, but it was in Dr. West's handout. It's a dimerization. Thank you. Shout out. I know I started moving really fast. I'm just like kind of freaked out that we're still on chapter 13 and we only have like 40 minutes left. But any questions about Diels-Alder? The general consensus I got from students was that Diels-Alder was fairly straightforward, especially because we had one of the students come up with something called the make or break method, and a lot of students found that super helpful. So, swag. Bless you. What about endo and exo? Okay, so endo and exo is in the handout that I'm going to send you guys, but basically endo is dashed and endo is always more stable. Okay. Deep breath. And we're going to do chapter 14, aromaticity. Wow. So aromaticity is a mouthful. There's a bajillion and a half rules, but it's pretty straightforward and it's mostly just memorization. So aromatic has to follow 4 rules: cyclic, planar, fully conjugated, and 4n+2. You know how I feel about the whole 4n+2 thing, so I say just no 2, 6, 10, 14. All of that is aromatic. Aromatic and anti-aromatic are actually really similar because the first 3 rules are exactly the same. The difference comes in rule number 4. And anti-aromatic is going to follow the 4n rule. I hate the 4n rule, so I just say 4, 8, 12, 16, etc. To be non-aromatic, it has to break any of the rules, aka not being sp3, odd number of electrons, not being planar, etc. Those rules are pretty straightforward. The complicated stuff is when we get into the heteroatom rules. So heteroatoms can choose to be sp2 or sp3. If you have multiple single bonded heteroatoms, they have to have the same hybridization. If you have a double bonded heteroatom, it has to be sp2 and it donates 1 single electron. And the 2 kind of exceptions are heteroatoms that are double bonded outside the ring. You can pretty much treat them just like carbocations. Boron is the same exact thing. It's always sp2 and it's always donating 0 electrons. So we can just pretend it's a carbocation. Putting all of these rules into action gives us this. So for this first one, we have nitrogen in there, and I lost my pencil and I found it. So here we could decide to be sp2 or sp3. So how do we choose? Well, if we are sp3, it's always going to be non-aromatic. If we're sp2, we have to count electrons. So if this was sp2, it donates 1 lone pair, which is 2, 4, 6 electrons. 6 electrons would be aromatic, so this is the better option. In this next example, we do the same thing, except if it's sp2 and donates 1 lone pair, we have 8 electrons, and 8 electrons is anti-aromatic. That sucks, so we pick sp3, which is non-aromatic. This one has 2 oxygens. They're both single bonded. Therefore, they have to both be sp2 or both be sp3. If they're both sp3, it's going to be non-aromatic. If they're both sp2, we have 2, 4, 6, 8 electrons, which would be anti-aromatic. So we choose sp3. And yes, so the choosing thing only has to do with heteroatoms and then planar versus not planar. But the planar versus not planar only applies to 8-membered rings or bigger. And I don't have an example of that, so I can draw one out. So, bless you. Wow, that's ugly. 1, 2, 3, 4. Okay, so this is cyclic, fully conjugated, 2, 4, 6, 8 pi electrons. So if it's sp2, excuse me, that's actually not what I want to write. If it's planar, it's anti-aromatic. If it's non-planar, it's going to be non-aromatic. So the more stable option would be non-aromatic. Ta-da! All right. The other ones are more of the same, so I'm just going to let it oh. Yeah, so Abel, I just saw that you wrote what do we do for 8-membered rings and above. I wrote it down just now. If you want me to re-explain it, I can definitely do that. But if you're good, just send me like a smiley face or something.
For the heteroatom rules, are these all of the rules? Because I remember writing down a lot more for chapter 14.
So they were written in a better, more organized way where it looked like a lot more, but it was much more thorough.
Mm-hmm.
So I can send you that notes as well, but those are probably better than this set.
Okay, so use the SI one because I think I have the SI one.
Mm-hmm.
Okay, cool.
So just to make sure, the thing with deciding between the two different forms of the anti-aromatic and non-aromatic, right? You only do that when it's 8 pi electrons or more, and if it has the heteroatoms, just those two.
Yes. And it's not 8 or more electrons, it's 8 or more carbons in the ring.
Oh, okay.
Cool. And then, yes, I will be sending you these notes later. I'm going to make them prettier. Okay. You're very welcome. 30 minutes for 15, 16, 17, 18. 4 more chapters. Jesus Christ. Okay, ready? We're going to do this thing. So, chapter 15, electrophilic aromatic substitutions. Half of this chapter is super, super, super easy. The rest of it is meh and thank you. My favorite meme ever was the "You're doing amazing, sweetie," and I used to quote that all the time. And you saying "You're doing great" really brought me back. So, anyways, we have 5 main reactions in chapter 15: alkylation, nitration, acylation, sulfonation, halogenation. Honestly, this stuff is straight up memorization. Not going to spend time on it. Pretty much same thing with directing effects, order of reactivity, all that kind of stuff. So the first 2 or 3 pages, 2 pages, is all just really memorization. This is where it gets interesting. So directing effects, this is where it gets interesting. So if you have multiple substituents already on the ring, you have to pick one of them to direct the substitution. And as it's written up there, the stronger activator will be the director. So I drew in the first example, we have an ortho-para activator, and we also have a meta deactivator. The activator is obviously a stronger activator than the deactivator is. So we are going to use the ortho-para positions for the OH. Sorry, someone said something and I got distracted. We are going to substitute the ortho and para positions in relation to the OH. And the reason that one is crossed out is because you are not going to substitute the position in between 2 pre-existing substituents, because it's too substituted, it's too hindered, it's too yucky. The other thing, and yes, I will zoom out to the other page when I'm done with this page. Just remind me if I don't do it. So the second one is a Friedel-Crafts reaction. Friedel-Crafts is not going to happen with a strong deactivator or NO2. Luckily, we don't have either of those things on this ring. This guy is an activator. This one is a weak deactivator. The activator still wins. So we're going to go ortho-para to this reagent. So we would have, of course I didn't give myself enough room. Why would I do that, you know? Ta-da. Yes, so I meant to say NH2. So Friedel-Crafts doesn't work with a strong deactivator or NH2. My bad. NO2 also doesn't work, but NH2 is not a deactivator. That's why I kind of put emphasis on it. All right, so for this third one, we're doing a sulfonation, and both of these guys are actually strong deactivators. So how do we pick which one is director? Well, if you look back at this list over here, we can see that CN comes before NO2, so it's technically less deactivating. So this guy becomes a deactivator, and we're going to do meta. So we could either get this, or we could get this. NO2 is a strong deactivator, yes. And H2 is not. All right. Whew. So this last one has an OH, which is an activator, and actually this ester is also an activator because the O is directly attached to the benzene ring, but the stronger activator is going to be OH. So we're going to go ortho para to that. This position is not going to work though because it is in between two substituents. So our two answers would be, oh my golly. Hold on. So I decided to be annoying. And since this is an alkylation, we can move this over and make it a better carbocation. So we turn that into this. So we would add this. I know it's ugly. I don't know what possessed me to make this question, but it is what it is, I guess. These guys are actually, hold on. Before I forget, ta-da. Welk. Again, these are just memorized. They're common names for benzene rings. Okay, so chapter 16, I believe I sent you guys a summary that looks almost exactly, if not completely exactly like this. So I want to just quickly go over that. The only thing that's different is this first one. So I am actually going to change this before I send it out to you. So gem dials, Dr. West did it a little bit differently the last semester than he did this semester. So this semester, he didn't really talk about the difference between acid and base. He talked about aldehydes versus ketones. So aldehyde prefers the gem diol form, whereas ketone prefers the ketone form. So that's all I changed for that first one. For acetals and ketols, I want to remind everyone that the reaction will only go all the way to the final product if there is an acid present, if there's no catalyst or base present. Sorry, I got distracted by another message. Very quickly, let's go back up to this one. This part is correct. So acid prefers ketone, base prefers gem diol. Both of those things are correct, but students get confused if we cover both of them. So I want you to focus more on the ketone versus aldehyde and less on acid versus base. And just to repeat what I said before, aldehydes prefer the gem diol form, and ketones prefer the ketone form.
Wait, so the base prefers gem diol, but what does that mean? Because I thought it was an aldehyde.
Ignore it. Just
Okay.
ignore it.
So just ignore what you wrote there for acid and base.
Yep.
Okay.
I'm just gonna cross it out when I send it to you again.
Okay.
Swaggy. All right. So what I was saying about acetyl-ketol. So acetyl-ketol reactions will only go to completion if there is acid present. If there's base or no catalyst, we are going to stop at the hemi. And then I just drew out what they look like, so ta-da. The imine reaction is when we replace the oxygen with a nitrogen and one R group. So we use a primary amine and we get the imine. I'm going to do enamine right quick. Enamine is like the imine reaction, but it's when we have a secondary amine. So secondary amines are going to form something different than the imine because they're too sterically hindered. So since they're so sterically hindered, you have to perform an elimination reaction and you get a double bond to one of the alpha carbons and a single bond to the nitrogen. Okay, back up to hydrazone. So the hydrazone is when you put in a hydrazine and you get a double bond to nitrogen, which is then also attached to an NH2. We could also have excess hydrazine and we get like this double ketone looking thing. It's really weird, it's really funky, it doesn't have a special name that you need to care about. So we're just going to, I almost said swag along and I really hate myself for even thinking that. It's fine. So the oxime formation, we react a hydroxylamine with a ketone and we add a nitrogen to the carbonyl and it has an OH as a substituent. The reason you use the NH to attack is because nitrogen is a better nucleophile than oxygen. Phenylhydrazone is exactly the same as the hydrazone. It just has a phenyl at the end. And then we have cyanohydrin, which is the one that I told you not to worry about. And then Dr. West covered it. And then I got annoyed. And then I said I didn't want to do it anyway. So just know the summary and then we're Gucci. Fun fact, I watched The House of Gucci the other day. It was painfully long and painfully boring. But, you know, yeah. Then again, I don't know how to appreciate anything that bores me. So, yeah. Lady Gaga was cool.
If it's boring, it failed as a story.
Right? That's what I'm saying. It was long. Like, after the first hour and a half, I just sat there and I was like, is it over yet? And then I was like, no, there's still another hour left. And I was like, That's also how I felt during Endgame, though. I was like, this shit's too long. I want to go home. I know. I'm sorry, but we're not here for Marvel controversy. We got to keep it going. Feel free to like email me.
That was definitely watch at home movie, not a watch at theater moment because I was getting kind of uncomfortable.
Yeah, and okay, Endgame I was more like paying attention to. Infinity War, I was like, can this be done already? I have places to be. I just want this to end. Anyway, moving on. So the Wittig reaction basically forms a ylide in the first part, and then it forms an alkene. If you remember the rosemary method, that's my favorite way of doing this. I thought that Joe said I had box issues, and I thought you meant like with this box method, and I was whole ready to use that as my transition to be like, you don't have to do the box method because there's a rosemary method. I'm going to pretend that's what you said just for the transition. So since Joe specifically had an issue with this box, I created a whole new method just for her. So what we're going to do is we're going to take our ketone and we're going to take our ylide and we're going to chop their heads off. We're going to throw the heads in the garbage because heads are gross. And we are going to put the arms and legs together. I hope you won't ever forget that because I can't. If you want more about this, watch my previous SI sessions. We spent like a really long time talking about this, but in all honesty, it's not too bad. 20 minutes run, I know. Okay, 17 and 18, chapter 17 is pretty cool because it doesn't involve a lot of thought. And if you hated chapter 17, hear me out because there's not much. Yes, you have to know the order of reactivity. That's just memorization. Naming, also memorization. So the only thing you kind of have to know is the reactions. But we have the Rosemary method again. So we go bam, leaving group, bam, hydrogen, nucleophile. Ow, I have the hiccups and they are mucho people.
What's the thing on top of the arrow? Because I want to write -1 hydrogen for the nucleophile.
Yes, so we minus 1 hydrogen. It was just an OH.
Oh no, I was wondering the name for like what's it called on top of the arrow.
Oh, reagent.
Okay,
it's
reagent.
just a, yeah, or nucleophile, whatever you want to say. So for the second one, we get rid of one of the nitrogen. We get rid of one of the hydrogens. The nitrogen is the nucleophile, and we get rid of the leaving group. So we end up with bam, bam, bam. Nope. For the last one, this whole, or not the last one, but second to last one, this whole thing is a leaving group. Get rid of the hydrogen. That's our nucleophile. So we give them one of those. Bam, pow. Bang. Yes, and these reactions have to go from less stable to more stable, except on your exam, Dr. West did one that went from more stable to less stable, and I was like, why would this happen? And he was like, it just happens. And I was like, all right. So if you see the question and no reaction isn't an answer, just do it as if it was, you know, a regular question. All right, go away, nucleophile. So we went from an OH to an ester. Therefore, this is a Fischer esterifications. And then someone had a really good question. If you go from a thioester to a thioester, is that considered a trans esterification? I'm going to say no. I don't believe so. I'm not 200% sure. But it's not going to, for this class, it's not the same. And then I don't know if I said one of these guys would be no reaction. But I didn't mean to say that. None of these are no reaction so far. Oh, okay, I see what you mean. So he did something like this on the exam, and the answer goes from an amide to a carboxylic acid. And we know that this won't happen, or it shouldn't happen, because it's going from the most stable to one of the most unstable. So we thought this wouldn't happen, but he had an exam question like this. So no, in theory, that we don't want to do that, but it could happen, if that makes sense. Yeah, so the SI sheet had a lot of like mixed, because I just had students practicing all kinds of reactions, and then what I tried to do is ask like which one of these goes from most stable to less stable and which one goes from less to more. just because I wanted you to have that practice in there. Ta-da. Okay, I'm sorry if I don't read your question or comment. This just kind of going pretty fast. All right. Number 5 is a Fischer esterification again, and this one is actually going to be a trans esterification. So I'll put that in here. So we get rid of this, get rid of the hydrogen. This guy is a nucleophile, so we get, bam. What makes it trans is just the fact that it goes from one ester to another ester. So it's still an ester, it's just a different ester. And for some reason, we call that trans esterification. All right, so the last one, we started with an ester, and we are adding our nucleophile, get rid of one of the hydrogens, so we get carboxylic acid. This is a base catalyzed hydrolysis, which means it is a saponification, and the details are in that box in the corner. Yes, so technically in number 5, the first one had a lower BP, or excuse me, the first one had a higher BP, and the second one has a lower BP because it's more branched, correct. Swag, okay. Again, just memorization stuff, to be completely honest. I'll give you a second to like screenshot or whatnot. Let's say that we can go from an amide to a carboxylic acid. It's not favorable, but we can do it. At this point, we're just going to say that there's not really anything that won't be no reaction. I mean, there won't be anything that would be no reaction for chapter 17, since Dr. West gave you a more to less stable one. I felt like I had a little bit of a stroke at that last little bit, but I hope you guys understood what I meant. If not, feel free to ask, but I do want to move on. Yes, so the only one, you're right. It's not that this would be no reaction, but the only way to make an acid halide is to use a carboxylic acid and to use one of those reagents. That's super specific. So you cannot make a alkyl halide any other way, or an acyl halide any other way. So these were in protecting groups, but they do other things as well. Yes. So, choking. This is not the time. We're going to skip lactones for a second because I can just send you this sheet. We've done it a bajillion times. I really want to get into chapter 18. So, chapter 18 has a bunch of reactions, and I'm pretty sure I sent you the version that had all the answers, but we're going to pretend that you don't have the answers, and we're going to run through it right quick. So, halogenation can be acid or base catalyzed. Acid catalyzed only adds one bromine. Base catalyzed is going to replace all the hydrogens on one side with bromine. Specifically, if you have something like this where it's 3 H's, you're going to go further and you're going to get the haloform reaction, which basically just turns into a carboxylic acid. And we have the haloform, which is this guy. The Hell-Volhard-Zelinsky has two different forms. So the form that does not have H2O, all we're doing is replacing OH with Br, and we're putting a Br on the alpha position. If we do have H2O, this becomes an OH again, and we still have a bromine here. Oh, I'm so sorry. Someone pointed out that I put two H's. Yes, I did mean to put two Brs. I am just stressed because I'm trying to finish in the next 8 minutes. The haloform reaction, someone asked what would it look like if there was no excess. So you're supposed to assume that there is excess, but if it says that there's only 1 mole, you just add 1 bromine. All right, so the Hell-Volhard-Zelinsky we did. Alkylation. Alkylation is going to be pretty straightforward. We have some kind of negative charge, which is going to act like a base. And then we're going to add this alkyl halide onto the alpha carbon. So we choose the more substituted alpha carbon, which is this one. And we have a 3-carbon chain. So we go bam, bam, bam. And we are only going to add once. We cannot add more than once. The acetoacetic and malonic ester synthesis are going to be kind of interesting. They're multi-step. So the first step is just going to be an alkylation. So it... Oh my, laptop is about to die. Okay. Crisis averted. We have bang, bang, and now we add this. In the next step, we change the OCH3s to OHs. If y'all don't stop leaving and coming back, I'm going to have a stroke. And then we do a decarboxylation. If you have no idea how to do a decarboxylation, please watch the SI session where I did it because it's kind of a lot. I'm just going to show you the product right now. So in a decarboxylation, essentially you get rid of this whole thing and you get OH, double bond, H, ta-da. And then you could put this into the ketone form, which would look like so. Ta-da. I also forgot to mention, Roche's kids, to be honest, halfway through chapter 16 and on, we are not on the same page. So Dr. Roche and Dr. West have been doing completely different things in those last few chapters. So I missed a lot of the reactions you need to know. Please see Katrina for that because there's some things that Roche goes over that I just completely have no idea about. And that's okay because today is my last day. Moving on. I thought that was funny, but nobody else did, but that's all right. So the malonic ester synthesis, first step again is just going to be our lovely little what do you call it? Alkylation. And thank you to the person who said they did find it funny. I appreciate you. So we just add the same alkyl group here. Second step, we replace the OCH3s with OHs, and now we have 2 of those. And we're going to do the same exact thing for the decarboxylation. We're just going to get rid of this whole guy. So we get oh my gosh. Okay. And we could tautomerize this, and we could get and scene. I will zoom out. Any questions, comments, and or concerns?
Yeah, for after this session, from your up all night tutoring, is that just for general questions? Is there no structure to it?
I mean, there's really no structure to any of my tutoring sessions. We all just come in and vibe. Or at least that's how it's supposed to be, but then sometimes people are like, can we just start at the top and go through everything? And I'm like, eh. So we kind of try to do that. But today is just purely questions. I didn't prepare anything.
Okay.
We're just doing what you guys want.
All right.
Yes, I
Thank
am going to post this, and I will send you the link. Have fun tutoring the one, Simon. I bet that's going to be a blast. If I don't see or like hear from any of you before your exam, I hope you have a wonderful day. You're going to do amazing. I heart you. I've had a wonderful semester. Thank you for being so wonderful. I don't say this to all my students, but you guys definitely were really great. So I know you guys are all amazing. Try not to freak out. Try to get a good night's sleep. Eat breakfast. Listen to some fun music before the exam, etc. Please reply to my emails. I didn't even see that you sent me an email. I will do that. Yeah, I do remember you sent me an email. Frick. I will get back to you. I forgot that happened entirely. Bye. Oh, guys are so cute. Hearts. Big hearts all around.